In the profound quiet of the cosmic ocean, amidst the ceaseless tides of light and gravity, there are worlds that remain shrouded in mystery, not by choice, but by the vast and indifferent geometry of space itself. We imagine the solar system as our neighborhood, a collection of familiar orbs tracing elegant ellipses around a shared hearth. Yet this perception is an illusion of proximity, a trick of the mind born from diagrams and maps that compress impossible gulfs into mere inches. The reality is one of profound isolation, of islands separated by deserts of vacuum so immense that to cross them is a feat of not just engineering, but of patience, of precision, and of a quiet, desperate hope against the relentless pull of a universe that does not wish to be traversed. Some of these celestial islands have known the briefest touch of our curiosity, a fleeting visitor from a distant blue dot that passed by, gathered whispers of data, and vanished back into the eternal night. Others have felt the tentative pressure of a lander, a mechanical emissary enduring hellish conditions to send back a postcard from an alien shore before falling forever silent. These are the frontiers within our own system, the planets that exist at the extremes of distance and environment, their stories only partially told, their secrets clinging stubbornly to the veils of cloud or the deep cold of remote orbits. To understand their solitude is to begin to comprehend the true scale of our solar realm and the audacity of the quest to know it. Consider the outer ice giants, Uranus and Neptune, realms of perpetual twilight. Their azure hues, so serene and distant in our telescopes, belie the ferocious dynamics of their atmospheres and the profound chill of their existence. They are sentinels at the edge of the known planetary domain, so far from the sun's warming embrace that the very concept of warmth becomes meaningless. Uranus orbits at a distance nearly 20 times greater than that which separates our world from the sun. A single languid circuit takes 84 of our years. Neptune, yet more remote, dwells 30 times further out, completing its grand tour in a century and a half. At such distances, the sun is no longer a defining celestial body, but merely the brightest star in a perpetually starry sky, a pinpoint of light that provides no meaningful heat, only a faint, cold reminder of the fiery heart around which all else revolves. To reach them requires not just a powerful rocket, but a precise alignment of the planets themselves, a celestial shortcut that opens only once in generations. The energy required to plunge so deep into the sun's gravitational well and then to slow enough to meet these distant worlds is staggering. It is a journey that demands sacrifice, often of time, of mission complexity, and of the very possibility of return. For most of human history, these worlds were but faint, star-like points, their true natures, their rings, their retinues of moons, their tilted rotations completely hidden. They existed in the realm of mathematics and prediction long before they existed in the realm of tangible reality. Even now, in an age of probes and digital eyes, they remain profoundly isolated. Only a single human-made object has ever beheld their cloud tops at close range, a solitary voyager on a one-way journey to the stars, who glanced at them in passing and carried on into the abyss. The data it returned is priceless, a foundational chapter in a story that has yet to receive a second paragraph. They are, in a very real sense, the forgotten giants, waiting in the silent dark for our next act of remembrance. Inward, toward the forge of the system, lies another kind of frontier, defined not by cold and distance, but by fire and gravitational fury. Mercury, the innermost world, is a planet of contradictions. It is a tiny, cratered sphere, barely larger than our moon, yet it is astonishingly dense. A metallic core clad in a thin, rocky shell, as if a giant's forge had stripped away its outer layers, leaving only the dense, iron heart. Its proximity to the Sun presents an engineering challenge of a different, more violent nature. To fall toward the Sun is easy. Gravity ensures that, but to arrive at Mercury with a speed slow enough to be captured into orbit or to make a controlled pass is a task of immense subtlety and counterintuitive planning. A spacecraft launched directly toward Mercury would be accelerated by the Sun's gravity to such phenomenal velocities that it would scream past its target, a helpless prisoner of momentum. To reach this sun-scorched world, one must not aim for it, but rather orchestrate a complex celestial dance, using the gravity of other planets, often our own Earth, and always Venus, as a brake, a gravitational moderator that bleeds away the excess speed imparted by our star. It is a journey of loops and curls, of patience measured in years, all to approach the target at a shallow, manageable angle. The Sun itself becomes the primary adversary, not just through its gravity, but through its radiant fury. Any probe daring to venture so close must be armored, shielded against temperatures that can melt lead and aluminum, its instruments protected behind layers of reflective, high-tech ceramics, its orientation locked in a perpetual ballet to keep that shield pointed squarely at the stellar inferno. To explore Mercury is to walk a tightrope across a furnace, a testament to our ability to calculate and insulate against forces that would obliterate any unprotected thing in moments. And then there is Venus, our so-called twin, a world that presents the most poignant and terrifying lesson in cosmic divergence. In size and bulk composition, Venus is Earth's near-identical sibling, born from the same primordial cloud. Yet its evolution charted a course into utter extremity. It is a world swaddled in a thick, toxic atmosphere of carbon dioxide, laced with sulfuric acid clouds that race around the planet at hurricane speeds, hiding the surface from prying optical eyes. Below this perpetual glowing overcast lies a landscape of crushing pressure and searing heat, a pressure 90 times that of Earth's at sea level, and a temperature stable at nearly 500 degrees Celsius, hot enough to render lead a shimmering liquid and to instantly crush and cook any terrestrial machinery. It is the very definition of a greenhouse effect runaway to its apocalyptic conclusion. Yet, for all its hostility, Venus holds a gravitational key. Its substantial mass makes it a perfect fulcrum for altering a spacecraft's trajectory, a gravitational slingshot used time and again to fling probes toward the inner solar system or to slow them for arrival at Mercury. We use its embrace, but we struggle to penetrate its secrets. Landers have descended through those yellow clouds, built like submarines or deep-sea diving bells to withstand the pressure, pre-cooled before entry to survive the heat just a little longer. They have returned grainy, ghostly images of a rocky, desolate landscape before the environment, indifferent and overwhelming, silenced them forever. After minutes, or if extraordinarily fortunate, just over an hour, Venus mocks our concepts of similarity. It is a warning etched in acid clouds and scorched rock, a demonstration of how thin the line between a living world and a sterile cauldron can be. Its exploration is a history of bold attempts, partial successes, and a lingering, profound mystery about how and why this sister world became such a beautiful, hellish antithesis to our own. The quest to reach these distant and difficult worlds is not merely a chronicle of rockets and robots. It is a fundamental expression of a human desire that stretches back to the first time a conscious mind looked up at a wandering star and wondered. It is the latest chapter in a story of measurement, of triangulation, of slowly pushing back the frontiers of the unknown. Centuries before any machine left Earth's atmosphere, the planet Venus played a pivotal role in one of astronomy's greatest quests, determining the absolute scale of the solar system. The key was the transit of Venus, a celestial alignment where Venus passes directly between the Earth and the Sun, appearing as a tiny, perfectly black dot traversing the solar disk. These events are rare, coming in pairs separated by over a century. In the 1700s, astronomers like Edmund Halley realized that by observing such a transit from widely separated points on Earth and meticulously timing the duration of Venus's passage, they could, through the principles of parallax, calculate the distance to Venus with unprecedented accuracy. This single measurement, the astronomical unit, would become the fundamental ruler for the cosmos, unlocking the true distances to all the planets. Expeditions were launched to the far corners of the globe, braving treacherous seas and unknown lands, all for the chance to capture a few precious hours of data as a small dot crossed a great disk. The 1769 transit, observed by Captain James Cook, among others from Tahiti, was a monumental international scientific effort. It was a humble beginning to the story of Venusian exploration, not with a rocket, but with a telescope, a precise clock, and a global collaboration to measure a shadow. From that moment, Venus ceased to be just a bright light in the sky. It became a place with a known distance, a world with physical dimensions, the first step on the long road that would eventually lead to the manufacture of a craft designed to survive its deadly embrace. The dawn of the space age transformed this intellectual curiosity into a tangible political and technological race. In 1961, the Soviet Union, already leading with the first satellite and the first human in space, set its sights on Venus with Venera 1. It was a simple probe, a sphere with solar panels and instruments, intended to fly past our neighboring world. It launched successfully, but en route, silence fell. Contact was lost, and the first emissary became a ghost ship, tumbling past its target without sending a single piece of data back. It was a stark reminder that the space between planets is not empty. It is filled with radiation, micrometeoroids, and the profound difficulty of maintaining control over a complex machine millions of kilometers away. The following year, the United States, desperate for a success in the face of Soviet achievements, prepared its own Venus mission, Mariner 1. The launch was tense, the stakes high. But shortly after liftoff, the rocket began to veer off course. A flaw in the guidance software, a missing overbar in the coded equations, caused the system to receive erroneous commands. To prevent a catastrophic, potentially populated impact, the range safety officer sent the destruct command. The rocket and its precious payload were obliterated in a fireball over the Atlantic. It was a failure born not of violent explosion or material weakness, but of a single minuscule human error in a line of code, a punctuation mark that doomed a multi-million-dollar mission and delayed a nation's ambitions. In these early faltering steps, the narrative was set. Exploration is a story punctuated by silence and fire, by the haunting loss of contact, and the sudden violent correction of a mistake. The void does not forgive, it merely waits, offering no consolation, only the cold equations of physics. Yet, the drive to reach out is resilient. Because planetary launch windows, the brief periods when Earth and the target planet are aligned for the most energy-efficient journey, recur only in cycles. Often every 18 months or more, the American team at the Jet Propulsion Laboratory had built a backup. Mariner 2 was not a purpose-built Venus explorer. It was a hasty adaptation of a Ranger spacecraft originally designed for lunar impact. These were days of improvisation and relentless pressure. The spacecraft was a simple hexagonal bus with solar panels, a dish antenna, and a suite of basic instruments, magnetometers, radiation sensors, and an infrared radiometer to scan the planet. In August of 1962, it lifted off, a second chance, riding on a pillar of flame. The journey was a testament to endurance, both of the machine and the nerves of its controllers. Its transmissions were weak, plagued by noise. A launch anomaly had left it off its intended path. A week into the flight, engineers composed a complex series of commands for a mid-course correction, a roll, a pitch, and finally the firing of its small engine to adjust its trajectory toward the intended rendezvous point in space. The signal was sent into the void. An hour later, data confirmed the maneuver had executed. It was a moment of quiet triumph in a mission fraught with anxiety. But the challenges were relentless. Days later, the spacecraft's attitude control, which relied on locking onto the Sun and the star Canopus for orientation, became confused. It lost its lock, tumbling blindly before an automated safety routine managed to reacquire its celestial guides. Then, a short circuit in one of its solar panels crippled its power supply. For a time, it limped along, its systems overheating as it drifted closer to the Sun. Yet, in a twist of cosmic irony, this proximity began to solve its power problem. As it neared the Sun, the single functioning solar panel began to generate more than enough electricity for the beleaguered craft's reduced needs. It was a fragile, wounded thing, but it was still alive, still on course. On December 14, 1962, Mariner 2 swept past Venus at a distance of about 35,000 kilometers. In its brief encounter, it made foundational discoveries. It detected no measurable planetary magnetic field, a surprising finding that hinted at fundamental differences in internal structure compared to Earth. Its infrared scan returned the most startling data of all. The temperatures across the planet, day and night side, were nearly uniform and scorchingly high, approaching 500 degrees Kelvin. The notion of a cloudy, perhaps swampy, or ocean-covered Venus, still popular in some science fiction, evaporated in that data stream. Venus was an oven. The celebration at the Jet Propulsion Laboratory was not just for a scientific first, it was the cathartic release of a nation proving it could indeed reach another planet. Mariner 2 was the first successful interplanetary probe, a pioneer that transformed Venus from a point of light into a world with measurable and deeply forbidding properties. The baton of rigorous exploration then passed back to the Soviet Union with a singular, monumental objective to land on the surface of Venus. The data from Mariner 2 and early Soviet flybys only confirmed the monstrous challenge. The Venera program's engineers were now tasked with creating a machine that could descend through an acidic, crushing atmosphere and survive, even briefly, on a surface hot enough to melt lead and under pressures equivalent to the ocean's deepest trenches. The landers they conceived were like nothing seen before or since. They were spherical pressure vessels, forged from titanium and thick metal alloys, designed not for the vacuum of space, but for an ocean of supercritical carbon dioxide. They looked less like spacecraft and more like deep-sea bathyspheres, built to implode-proof standards. Each was encased in a spherical aeroshell for the initial fiery entry, then would deploy a parachute for the slow, agonizing descent through the dense, hot clouds. In June 1967, Venera 4 began this daring plunge. For 93 minutes, it radioed back data as it fell: temperature, pressure, atmospheric composition. It was a torrent of new information, but it fell silent while still 28 kilometers above the inferred surface. The heat had not killed it. It had simply run out of battery power, its chemical cells exhausted before it could complete its journey. Yet, by extrapolating the final data points, Soviet scientists made a shocking calculation. The surface pressure was not the 20 Earth atmospheres some had predicted, but a staggering 75 atmospheres or more, and the temperature was around 500 degrees Celsius. Each attempt refined the design. Venera 5 and 6, launched in 1969, were built stronger, with smaller parachutes to hasten the descent and conserve precious battery life for the surface. They too transmitted invaluable atmospheric data during their fall, but were crushed by the immense pressure before reaching the ground. The program was a brutal exercise in incremental engineering, each failure teaching a lesson that was incorporated into the next, more robust design. It was a war of attrition against an environment of almost cartoonish hostility, fought one circuit board, one pressure seal, one heat shield at a time. The relentless iteration culminated in the triumph of 1975. Venera 9 and 10 were a new generation orbiter-lander combinations. The orbiter would act as a sophisticated relay station, circling the planet and capturing global data, while the lander, encased in its protective sphere, would make the fateful descent. After a 4-month cruise, the landers separated. They entered the atmosphere like blazing comets, their heat shields glowing against the toxic yellow sky. As they slowed, they deployed parachutes, then jettisoned them in the lower, soupy atmosphere, relying on a simple disc-shaped aerobrake to control their final fall. On October 22, 1975, Venera 9 touched down on a rocky slope. It had been pre-cooled in space to give it a thermal buffer, and a circulating fluid cooling system fought a desperate, losing battle against the hellish heat. For 53 minutes, it defied the impossible. A camera, protected behind a lens cap that was pyrotechnically ejected after landing, began to scan its surroundings. The image that emerged, line by painstaking line, on monitors in the Soviet control room was history-making. The first photograph ever returned from the surface of another planet. It showed a stark, rocky landscape strewn with flat, slab-like rocks under a diffuse, gloomy light filtered through the thick clouds above. A design flaw meant a second camera's lens cap failed to eject, but one was enough. 3 days later, 2,000 kilometers away, Venera 10 landed and repeated the feat, though its second camera also suffered the same lens cap malfunction. Both landers, through their brief, heroic windows of operation, transformed Venus from an abstract inferno into a real place. We could see it. We had stood upon it, if only through the electronic eyes of a machine that expired minutes later, its mission complete, its data secure. These were not just scientific successes, they were acts of almost inconceivable engineering, fortitude, monuments to human perseverance in the face of a universe designed to destroy complexity. The next great leap in unveiling Venus required seeing through its perpetual shroud. Optical cameras were useless for mapping the global surface. The answer was radar. In 1983, the Soviet Union launched Venera 15 and 16, twin orbiters equipped with synthetic aperture radar. For 8 months, they systematically scanned the northern hemisphere of the planet, from the pole down to about 30 degrees north latitude. Their radar pulses penetrated the clouds, bouncing off the solid ground below and returning echoes that were translated into topographic maps. A new Venus emerged from the data, a world of vast volcanic plains punctuated by strange pancake-like domes called coronae and towering highland regions like Ishtar Terra and Aphrodite Terra, the size of continents on Earth. It was a world sculpted not by water erosion but by volcanism on a planetary scale. The thick atmosphere acted as a protective blanket, preventing all but the largest meteorites from reaching the surface, which explained the surprising paucity of impact craters. Yet, curiously, the telltale signs of plate tectonics, the sliding, colliding crustal plates that constantly reshape Earth, seemed absent. Venus appeared to be a single unbroken lithospheric shell. The question then became, was this a dead world, its volcanic fires long extinguished, or merely a sleeping one? NASA, which had taken a secondary role after Mariner 2, re-entered the Venusian arena with a mission of unparalleled ambition. In 1989, the Space Shuttle Atlantis lifted off, its cargo bay containing the Magellan spacecraft. Named after the great circumnavigator, Magellan's mission was to map the entire surface of Venus with radar at a resolution far surpassing the Soviet maps. To control costs, the probe was famously built from a collection of spare parts and hardware left over from other missions. Voyager, Galileo, Ulysses, it was an engineer's patchwork masterpiece. After a 15-month cruise, it arrived at Venus and entered a precise elliptical orbit. Following the resolution of some initial software issues, it began its work. For 4 years, Magellan's radar mapper sent pulses downward, crafting a global portrait of stunning clarity. The images revealed a world of breathtaking geologic drama, vast lava flows that stretched for thousands of kilometers, intricate networks of channels carved by rivers of molten rock, thousands of volcanoes of all sizes, and those peculiar, wrinkle-like tesserae terrain that suggested a complex, tortured history of compression and stretching. The near absence of impact craters allowed scientists to perform a kind of cosmic dating. By counting the few craters that existed, they estimated the average surface age of Venus to be roughly 500 million years. This led to a provocative, though still debated, hypothesis that around 500 million years ago, Venus underwent a cataclysmic global resurfacing event. Perhaps the planet's internal heat, unable to escape through plate tectonics, built up until the entire crust succumbed in a planet-wide volcanic paroxysm, repaving the world in fresh lava. It was a vision of apocalypse on a planetary scale. Yet, for all its evidence of past fury, Magellan could find no definitive proof of ongoing volcanic activity. Was Venus geologically dead or simply biding its time? The question of a living Venus drew the European Space Agency to launch Venus Express in 2005. This orbiter, a repurposed design from the Mars Express mission, focused not on the surface, but on the dynamic, complex atmosphere. For 8 years, it studied the composition, circulation, and chemistry of the Venusian air. It made tantalizing, ambiguous discoveries. It registered a sharp, temporary spike in atmospheric sulfur dioxide, a gas typically associated with volcanic eruptions. While this could be explained by changes in atmospheric circulation, it could also be a plume from an erupting volcano. Its infrared instruments detected hotspots on the surface, regions that appeared to have higher thermal emissions, again potentially linked to fresh lava flows. Most intriguingly, it observed short-term fluctuations in the surface temperature at specific locations, changes that occurred over just a few Earth days, hinting at possible active lava lakes or other thermal anomalies. The evidence was circumstantial, a collection of clues pointing toward a volcanically active present, but no smoking gun, or rather no erupting volcano, was caught in the act. When Venus Express ended its mission in 2015 with a series of daring dips into the upper atmosphere, it left behind a compelling mystery. Since then, the torch of Venus exploration has dimmed. Elaborate plans for landers, balloons, and advanced orbiters exist on drawing boards and in proposal documents, but as of now, no major funded mission is en route. Venus, the hellish sister, once again waits in patient silence, its secrets guarded by acid and heat, visited only by spacecraft, using its gravity to bend their paths toward other destinations, a celestial waypoint in the grand tour of the solar system. The technique of using a planet's gravity to alter a spacecraft's trajectory, the gravitational slingshot or assist, is now a cornerstone of interplanetary travel. But its first intentional use for a planetary encounter was a masterpiece of celestial mechanics applied to one of the hardest targets, Mercury. The architect was Italian mathematician Giuseppe Bepi Colombo. He realized that a spacecraft could use a flyby of Venus not just to slow down, but to set up a resonant orbit with Mercury, allowing multiple flybys of the innermost planet with a single launch. This was the trajectory chosen for NASA's Mariner 10 in 1973. The journey was a delicate one, fraught with peril from the sun's overwhelming influence. Just 10 days after launch, as the spacecraft executed a routine course correction, a bizarre problem emerged. Its attitude control system, which used a sensor locked onto the bright star Canopus for orientation, became confused. A flake of white paint, shaken loose from the spacecraft during the engine burn, was floating nearby, reflecting sunlight and mimicking a star. The sensor locked onto this phantom, causing the spacecraft to tumble. An automated backup procedure eventually found the real Canopus, but the paint flake ghost haunted the mission thereafter, a trivial terrestrial material causing cosmic-scale navigation headaches. To reach Mercury, Mariner 10 had to perform a delicate dance with Venus's gravity, which acted as a brake, reducing its solar orbital energy and bending its path inward. When it finally arrived at Mercury in March 1974, it did not orbit. It flew past at a sharp angle, its trajectory shaped by the sun's fierce pull. The first images revealed a world that looked hauntingly familiar, a heavily cratered moon-like surface. But Mercury held surprises. Despite being the smallest planet, it is extraordinarily dense, suggesting a massive iron core comprising nearly 85% of its radius. Its surface also bore immense, cliff-like faults called lobate scarps, some hundreds of kilometers long and up to 3 kilometers high. These scarps are thought to be wrinkles formed as the planet's huge iron core cooled and contracted over billions of years, causing the crust to buckle and fracture. Mariner 10 was a mission perpetually on the edge of failure. Its tape recorder stuck, its attitude control was finicky. Engineers learned to use the subtle pressure of sunlight itself on the spacecraft's high-gain antenna and solar panels to help maintain orientation, a technique called solar sailing in its most rudimentary form. Despite it all, the probe made 3 flybys, mapping about 45% of the surface. It discovered a tenuous exosphere, mostly helium, atoms blasted from the surface by the solar wind. Months after its final encounter, it ran out of attitude control fuel and fell silent, becoming a permanent inert companion to the sun it dared to approach. It would be over 30 years before Mercury received another visitor, a gap that speaks to the immense difficulty of the endeavor. The Messenger mission, Mercury's surface, space environment, geochemistry, and ranging, was conceived not just to fly by, but to orbit. This presented monumental thermal and design challenges. The solution was a revolutionary sunshield, a large rectangular blanket made of heat-resistant ceramic cloth, mounted on a titanium frame. This shield would always face the sun, protecting the bus and instruments behind it in a permanent shadow. Messenger had no moving dish antenna. Instead, it used a fixed, phased array antenna that could electronically steer its radio beam. Launched in 2004, its journey was a masterpiece of gravitational choreography. It flew by Earth once, Venus twice, and Mercury itself 3 times. Each encounter meticulously bleeding off speed, like a spacecraft applying celestial brakes, before it was slow enough to be captured into orbit in 2011, a 7-year journey to its destination. From orbit, Messenger completed the global map. It revealed Mercury to be a world of startling contrasts. The giant Caloris Basin, a colossal impact crater over 1,500 kilometers across, first glimpsed by Mariner 10, was fully mapped, its intricate fracture patterns telling a story of unimaginable seismic waves reverberating around the planet. Perhaps its most profound discovery lay in the permanent shadows of craters at Mercury's poles. Because the planet's rotational axis has almost no tilt, the sun never rises above the rims of these deep polar craters. Within these cold traps, radar signals from Earth had hinted at reflective material, and Messenger confirmed it. Vast deposits of water ice mixed with dark organic material, preserved for billions of years in the freezing darkness, just a short cosmic distance from the solar furnace. This ice, likely delivered by comets, is a testament to the complexity of planetary environments. Messenger operated for 4 years in Mercury's scorching neighborhood before, its propellant exhausted, it was commanded to impact the surface in 2015, adding a new human-made crater to the ancient landscape. The torch has now been passed to Bepi Colombo, a joint mission by the European and Japanese space agencies, named in honor of the trajectory pioneer. Launched in 2018, it is on its own multi-year, multi-flyby journey, carrying a suite of advanced instruments to probe Mercury's magnetic field, composition, and geology in even greater detail when it arrives in orbit in 2025. The innermost world, once a blurred mystery, is slowly yielding its secrets to patience and gravitational ingenuity. Beyond the rocky inner planets and the asteroid belt, beyond the majestic gas giants Jupiter and Saturn, lie the frontier realms of the ice giants, Uranus and Neptune. Their exploration is the story of a singular, once-in-a-lifetime opportunity seized by a pair of resilient robots. In the late 1970s, a rare geometric alignment of the four outer planets occurred, a configuration that happens only once every 175 years. A spacecraft launched at the right time could use each planet's gravity to swing on to the next, a grand tour that would be impossible under any other circumstances. This was the genesis of the Voyager program. Voyager 2, launched first on a slower trajectory, was the one destined for the ice giants. In January 1986, after a 9-year journey from Jupiter and Saturn, it arrived at the pale blue-green disk of Uranus. The planet presented itself as an oddity among oddities. Sometime in the deep past, a colossal impact, or perhaps a series of gravitational interactions, knocked Uranus onto its side. Its rotational axis is tilted a staggering 98 degrees relative to its orbit. Thus, for parts of its 84-year orbit, one pole points directly at the Sun, experiencing 42 years of continuous daylight, while the other lies in utter darkness. Its rings and many of its moons orbit in this tipped-over plane, making the system appear to roll around the Sun like a celestial wheel. Voyager 2 discovered 11 new moons, a complex system of dark, narrow rings and a magnetic field that was both strong and wildly misaligned, offset from the planet's center and tilted at a 59-degree angle to its rotational axis. The planet's atmosphere, viewed in visible light, appeared as a nearly featureless aquamarine haze, a consequence of methane-absorbing red light and the particular seasonal quiet during Voyager's visit. It was a world of profound stillness, its weather locked in a deep freeze. But the king of its moons was Miranda. Seen up close, this medium-sized moon was a geological jigsaw puzzle. Its surface was a chaotic assemblage of giant fault canyons, terraced layers, and bizarre chevron-shaped regions. It looked as though it had been shattered and carelessly reassembled. The leading theory today is not a single shattering impact, but intense tidal heating and tectonic forces from Uranus's gravity, which may have caused partial melting and dramatic overturning of Miranda's interior, creating its patchwork landscape. As Voyager 2 departed, looking back at the crescent Uranus with the Sun behind it, it discovered two new, faint rings illuminated like cosmic dust lanes. Then it turned its instruments toward the final planetary target, Neptune. The 3-year cruise from Uranus to Neptune was a time of intense preparation at the Jet Propulsion Laboratory. The challenges were unprecedented. At Neptune's distance, 30 times further from the Sun than Earth, sunlight is only 1/900th as intense. To photograph the planet and its moons, Voyager 2's cameras would need to use long exposures. But the spacecraft was moving at over 60,000 kilometers per hour relative to Neptune. A stationary camera during a long exposure would result in a hopelessly smeared image. The engineers devised a brilliant solution. They programmed the entire spacecraft to swivel smoothly and precisely during the exposure, panning its cameras to compensate for its own motion, a technique called image motion compensation. It was a flawless execution of celestial marksmanship. In the summer of 1989, as Voyager 2 approached, the world watched, captivated. This was before the Internet's instant data flow. Images appeared line by line on monitors, each new strip of pixels building anticipation in labs and living rooms. Neptune revealed itself as a world of dynamic beauty, a deep azure sphere banded with white clouds. Unlike Uranus, it has a significant internal heat source, radiating more than twice the energy it receives from the Sun, which fuels a tempestuous atmosphere. Voyager measured the fastest winds in the solar system, screaming at over 2,000 kilometers per hour. It observed high-altitude cirrus clouds of methane ice casting shadows on the blue cloud deck below. Most spectacularly, it found the Great Dark Spot, an Earth-sized anticyclonic storm in the southern hemisphere, a sibling to Jupiter's Great Red Spot. But Neptune's weather is ephemeral. When the Hubble Space Telescope looked for the Great Dark Spot just 5 years later, it was gone, though a new one had appeared in the northern hemisphere. The mission's final planetary act was a close flyby of Neptune's largest moon, Triton. This world immediately declared its alien nature. It orbits Neptune in a direction opposite to the planet's rotation, a retrograde orbit that strongly suggests it was not born with Neptune but was captured from the Kuiper Belt, the vast reservoir of icy bodies beyond. Triton's surface, a mottled pinkish hue from nitrogen and methane ice, was astonishingly young and complex, with few craters. It showed evidence of cryovolcanism, ice volcanoes that erupt water, ammonia, or nitrogen slush. Cantaloupe-like terrain, vast smooth plains, and dark streaks from geyser-like plumes hinted at a subsurface ocean and ongoing geological activity, making it one of the most intriguing icy worlds in the solar system. With the Triton encounter complete, Voyager 2's planetary mission ended. Its cameras were powered down, its tape recorders fell silent, and it joined its twin Voyager 1 on an eternal journey into interstellar space. To this day, they remain the only envoys to have visited the ice giants, their brief encounters constituting our entire library of close-range data on these distant blue worlds. The story of solar system exploration does not end with Neptune. The discovery of the Kuiper Belt, a vast disk of icy remnants from the solar system's formation, redefined our planetary neighborhood and demoted Pluto from its status as the 9th planet to the king of this icy realm. The mission to explore it, New Horizons, was an exercise in speed and patience. Launched in 2006 on a mighty Atlas V rocket, it left Earth faster than any probe before it, crossing the Moon's orbit in just 9 hours. A gravity assist from Jupiter a year later hurled it toward Pluto on a direct trajectory. For most of its 9.5-year journey, it hiberned, a silent arrow shot into the dark. Its arrival in July 2015 was a global event. Pluto, seen up close, was a revelation. It was not a dead, cratered ice ball, but a stunningly complex and vibrant world. Vast plains of frozen nitrogen, patterned with polygonal cells, suggesting slow convective churning, abutted mountain ranges made of water ice, hard as rock at Pluto's temperatures. Evidence of tectonic forces, possible cryovolcanoes, and a thin, hazy atmosphere of nitrogen extended high above the surface. Its large moon, Charon, revealed deep canyons and a surprisingly varied surface with a dark, reddish polar cap. The two form a binary system, locked in a mutual dance around a common center of gravity. From Pluto's surface, Charon would hang motionless in the sky, a giant companion world. The data from the brief flyby was so rich it took over 16 months to trickle back to Earth at painstakingly slow data rates across the vast distance. New Horizons, its primary mission a spectacular success, was then redirected to a second Kuiper Belt object, Arrokoth, which it flew past in 2019. This primordial contact binary object, looking like a flattened snowman, provided a pristine fossil from the solar system's birth. New Horizons continues its journey outward, a final testament to the era of first reconnaissance, carrying our curiosity to the frozen fringes of the sun's domain. All these journeys, all these glimpses of alien worlds are conducted under the watchful, driving influence of the sun itself. Our star is not a static backdrop. It is the dynamic, violent, life-giving engine of the entire system. Its light enables life, but its fury also shapes and threatens it. The solar wind, a constant supersonic stream of charged particles blowing from the sun's corona, carves a vast bubble in the interstellar medium called the heliosphere, within which all the planets reside. Earth is protected from the solar wind's full brunt by its magnetic field, which deflects the particles, channeling some to the poles to create the auroras. But the sun's mood is not constant. It follows an 11-year cycle of activity marked by the rise and fall of sunspots, cooler, magnetically active regions on its surface. These magnetic disturbances can unleash solar flares, intense bursts of radiation across the electromagnetic spectrum, and coronal mass ejections, CMEs, billion-ton clouds of magnetized plasma hurled into space at millions of kilometers per hour. When a CME is directed at Earth, it can compress our magnetosphere, induce powerful electrical currents in power grids, disrupt satellites and communications, and paint the skies with auroras that descend to low latitudes. The Carrington event of 1859, the most powerful geomagnetic storm on record, caused telegraph systems worldwide to fail, with operators receiving shocks and papers catching fire from induced currents. A similar event today, in our hyper-electrified, satellite-dependent civilization, could cause trillions of dollars in damage and catastrophic, long-lasting disruptions. Understanding the sun is no longer just a matter of astrophysical curiosity. It is a practical necessity for our technological survival. The quest to understand our star has spawned a fleet of solar observatories. The Solar and Heliospheric Observatory, SOHO, launched in 1995 and stationed at the Lagrange point where Earth and Sun's gravity balance, has provided an uninterrupted quarter-century watch on the Sun. Its coronagraphs, which block the blinding solar disk to reveal the faint corona, have become iconic, showing CMEs blossoming like cosmic flowers and the planets marching in procession against the stellar wind. The Solar Dynamics Observatory, SDO, launched in 2010, stares at the Sun in high definition across multiple wavelengths, each revealing different temperatures and processes in the solar atmosphere, from the 6,000 Kelvin photosphere to the multi-million degree corona. It captures the mesmerizing dance of plasma along magnetic field lines, the formation and eruption of sunspots, and the physics of solar flares in exquisite detail. Yet, a fundamental mystery persists: the coronal heating problem. Why does the Sun's outer atmosphere, the corona, reach temperatures over 1,000,000 degrees Kelvin, while the visible surface below is a relatively cool 5,800 Kelvin? The energy must come from the convective turbulence below, transferred upward via the Sun's complex magnetic field, but the precise mechanism, whether nanoflares, magnetic wave heating, or something else, remains elusive. To solve such mysteries, we must go closer. The Parker Solar Probe, named for the visionary physicist Eugene Parker, who predicted the solar wind, is humanity's first mission to touch the Sun. Launched in 2018 on a mighty Delta IV heavy rocket, Its mission is to fly through the Sun's corona itself. Protected by a revolutionary carbon composite heat shield that withstands temperatures exceeding 1,400 degrees Celsius, the probe will perform 24 increasingly close orbits over 7 years, using 7 Venus flybys to gradually tighten its loop around the Sun. At its closest approach, it will come within 6.2 million kilometers of the solar surface, moving at nearly 700,000 kilometers per hour, fast enough to fly from New York to Tokyo in under a minute. Within the corona, it will directly sample the particles and magnetic fields, seeking the origins of the solar wind and the mechanisms that heat it. Its initial data has already been revolutionary, revealing a surprisingly turbulent and structured solar wind near the Sun with sudden magnetic reversals nicknamed switchbacks. Each pass brings new, unexpected insights, reminding us that to know a star, one must venture into its fiery atmosphere. As we look beyond our own system, we see that the Sun is ordinary. It is one of hundreds of billions of stars in the Milky Way, a main sequence Gi-type star in the tranquil middle age of its 10-billion-year life. Studies of other stars reveal the full spectrum of solar behavior. Young, rapidly rotating stars can unleash superflares thousands of times more powerful than anything in our historical records. The small, common red dwarf stars, which make up the majority of stars in the galaxy, are prone to frequent, violent flares that could strip the atmospheres from any orbiting terrestrial planets, complicating the search for habitable worlds. Our Sun, by comparison, is remarkably stable, a benevolent, steady anchor for our fragile oasis of life. This stability, however, is not eternal. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core, swell into a red giant, engulfing Mercury and Venus, and likely rendering Earth uninhabitable before shedding its outer layers and leaving behind a cooling white dwarf remnant. The grand narrative of our solar system, from its coalescence from a protoplanetary disk to its eventual dissipation, is inextricably tied to the life cycle of its star. The exploration chronicled here, from the first grainy images of Venusian rocks to the delicate ice of Mercury's poles, from the chaotic majesty of Neptune's winds to the frozen, geologically active plains of Pluto, represents more than a catalogue of scientific achievement. It is a testament to a species that refuses to be bound by its atmosphere, that builds machines of exquisite fragility to withstand environments of unimaginable extremity, all for the sake of a picture, a dataset, an answer. Each mission is a message in a bottle hurled into a cosmic ocean, a declaration that we wish to know our place. The voids between worlds are immense. The challenges of heat, cold, radiation, and time are daunting, and the failures are many. But the trajectory of the past 6 decades is clear. We are moving outward, learning, adapting, and deepening our understanding of this complex, dynamic, and beautiful system we call home. The planets are no longer just points of light. They are worlds with history, personality, and mystery. And as the voyagers sail silently into the interstellar dark, as Parker dives repeatedly into the solar forge, and as new probes are conceived for the ice giants and the ocean worlds, the story continues. It is a story with no final chapter, only an endless horizon of questions waiting for the next generation of explorers, human and robotic, to venture forth and write, with data and discovery, the next line. For now, the silent dance of the planets continues, watched by our electronic eyes, a ballet of gravity and light that has unfolded for billions of years and will continue long after our own star has faded. It is a humbling, awe-inspiring spectacle, and our great fortune to have begun to see it, to understand it, and to be a conscious part of its grand unfolding story. Good night.